Sometimes it's called the work energy theorem, but the basic principle that I've kind of written up, and it's been in the note a few times, is that the work done on an object is equal to the energy gained. We don't really have any equations for energy yet, but we know work. Work is always Ft cos the angle between them. So if we're talking about the energy to lift something, we can say that Ft cosine the angle is equal to the energy to lift. Now, here it gets a little cool. If we're talking about lifting something, I'll switch colors, the force to lift something you have to match gravity. If you think about starting from rest, you have to lift harder than gravity to get it moving, but then to stop it from moving, you lift a little bit lower than gravity. Overall, to lift something, you just have to match gravity. Maybe you lift a little bit harder for a bit, maybe you lift a little lighter for a bit, but if we average it out, to lift it, you have to match gravity. Because we're talking about lifting, we replace the letter D with the letter H for height. And then the last part is, if we lift something straight up, so say we've got a box, if we lift it straight up, the D is pointed straight up. To lift it, if we think about forces, the force you do to lift it is also straight up. So we can say that the angle between those is 0 degrees. That means that our energy, it was Ft cos the angle. Instead of F, I'm going to write mg. Instead of D, I'm going to write h for height. And then we multiply by the cosine of 0 degrees, since they're in the exact same direction. The cosine of 0 is exactly 1, so this means that our energy to lift is mgh. And to be clear, we put a little g with this for gravitational. Now, realistically, we don't always lift things straight up. So let's say we've got something heavy, it's down here, and we eventually get it way up. Maybe there's a shelf or something here. So we eventually lift this heavy mass from down there. We carry it on an angle so that it ends up here. In a case like that, technically speaking, we've moved it on this funny angle. We've moved it a distance that isn't h for height. Height would be here. So we've moved it a bigger distance, but because we moved it on a funny angle, we exert less force over that greater distance. So if we think of our equation, work was equal to F times D. When we move things on an angle, we move them a greater distance, so the distance numbers go up, but because we're moving it on an angle, the force numbers go down. So they kind of cancel each other out. Really, what's important for this gravitational potential energy or gravitational field energy is that to figure out the amount of energy, we can simplify it to mgh, regardless of what path it takes. The h is the overall change in height. Even if it goes on a funny longer path, we just need to worry about that overall difference in height, mgh.